Okay, so I made it. I don't know what's up with the second projector, but it doesn't matter, we have a good one anyway. So last class I promised we'd do a couple of things today. One is to finish up this game, which I just finished about 15 minutes ago now. And the other is to maybe get started on studying recursion, leading us into the study of algorithms. So, if you remember this game, last time we left it, it started out in a state that you were playing immediately. Usually not what you want. You usually want some start screen. So I've put on a start screen. It also was a game where the missiles, the so-called missiles, were just little red dots drawn as circles. That was just to get us going. I've improved the graphics, I guess you could say. And then there's a whole cycle of you play for a while, your bases die, and then it's game over. And I've done a couple of other touch-ups, nothing too big. So click anywhere to start. So you click, that goes away, and then the missiles start coming. So now the missiles are things that look a little bit more like what you would call a missile. Some of the game mechanics were changed a little bit. If you remember last time we had missiles that split. That was something we did in class. But they would split even if they were at the bottom of the screen, which led to some strange behavior. Now they won't split if they're in the bottom half of the screen. Okay. And there's a little bit of the maximum arrival rate of missiles has gone down a little bit. So we don't get these giant firecracker-like explosions that go across the whole screen, although gets pretty crowded up there. I seem to have neglected my left base. Well, because there's no code to tell them to do otherwise yet. So, bug, game killing bug. Okay. B dot health divided by 3. All right, let's open it up and see it. So this seems to have happened because the health went negative. My guess would be. Or let's say so let's just kill everything, just so we can see the game over screen. I'll turn up the volume. We get a game over, a little pause, and then a click to start the game. So a full cycle, and if we click, it just resets the game. Okay, so I told you I'd just quickly walk you through the code to see how all of this works. Maybe the most interesting part of the code, which would be useful for some of you guys, is the code for the missiles, drawing the missiles. So if you look at that, that's in the missile class. There's a missile image that gets loaded, missile1.png. You can take a look at that. So there's this image of the missile that we use. It's pointing off to the right. That's on purpose. It's pointing, for our purposes, that's in the direction of the positive x-axis. And you notice that when we launch these missiles, they don't just travel through the air pointing off to the right. They're actually pointing in the right direction. So the question is, how do we do that? All right. So we do that by rotating this image. So remember, the lifetime of a missile is the user clicks somewhere, that's the target of the missile, and then it will go from the base, the starting point, to that target in a straight line. So that means we can get away with one rotation to point the missile, that image, to have it point in its direction of travel. And so that's what we do here. First we get the vector from the target, from the current location to the target. That's the code we always use to get these vectors. And now we want to compute the angle of that vector. So we're looking at, we have an image which points like this on the x-axis off to the right, and this is the starting location, and we want it to go over here, and what we've got is this vector here. This is v at 0, and this is v at 1. And we're looking for this angle here, because that's how much we have to rotate this missile to have it point in the right direction. So when you have a vector and you want to get an angle that it makes with, say, the x-axis, anybody know how to do that? Yeah.
Isn't like a tan of VO on V1?
So the tan is a thing that takes an angle, and it gives you this length divided by this length, right?
Sorry, tan minus 1.
Yeah. So we want the opposite. We have this length and we have this length. What we want is this angle here. And there's usually in math libraries, there's a 2-argument version. So we want the arctan. So the thing that takes these 2 lengths and converts them to this angle. And in math libraries, there's a 2-argument version that gets around the fact that there are different angles that have the same value of the tangent function when you're either in the positive axis or the negative axis. So we just have to feed it these 2 lengths here. This length, the v1 and v0, and it gives us the angle. So there it is, alpha. Now, the first thing you'll try is then rotate the image by alpha to get this to work. And you'll see that that doesn't work at all. The image hardly gets rotated at all, and that's because when we talk about tangents and sines and cosines, we're usually measuring angles as multiples of pi. So this really is some number that you get here is a number between plus pi, which would be an angle that goes all the way up here, to minus pi, which is an angle that goes all the way here. But the pygame rotate function wants an angle in degrees. It's multiples of 360. Yeah?
Why does the rotation function take its argument in degrees?
Because game developers like angles in degrees, and math library developers like angles in radians. It's just the convention in those 2 disciplines. It's a good question, though, because this different units is not as a case of is an important thing that causes a lot of problems. For instance, one of the rocket explosions, in historical ones, was caused by the fact that engineers were measuring things in meters, or were measuring things in feet, and physicists were measuring it in meters, and the two failed to do the conversion correctly. That cost only a few $1 million of exploding rockets to find that bug. So it's not a small thing, it leads to bugs. Luckily, this is a bug that you'll catch immediately, because rotations of pi angles or minus pi angles are almost not rotations at all. They're very degrees are not very much at all. Yeah. Sorry, plus pi. So if your vector looked like this, then you'll get back something that's very close to pi, plus pi, and if your vector looked like this, you'll get back something that's very close to minus pi. And if your vector looks like this, I don't know whether you get plus or minus pi, but it doesn't really matter. Okay, so then we do the rotation, and that's the image that we use for this missile from now on, because it'll always be pointing in the right direction for this missile. In some other situations, this is the kind of thing that you would actually compute at every frame. It's fast enough to do that and do the rotation. For example, assignment 7 had this cat chasing around a mouse. You know, if you wanted to make it look really fancy, the cat would sort of be facing the mouse and not just translating itself around. So you could do that this way. Okay. Any questions about that? So there's a piece of code for you to borrow if you need for your assignment. And about the only other big things, the only other major change was we got all the states worked out for this game. And the states look like this. And there's a state called pre-play. That's this click to start the game screen. There's a state called playing. That's where you're actually playing the game. And there's a state called game over. And that's where you're looking at the screen that says game over, and there's a sound playing. And the way the transitions between these states work are, if you're in pre-play and the user clicks the mouse, then you move into the playing state. If you're in the playing state and the health of both bases is less than or equal to 0, then you're in the game over state. And from the game over state, there's a transition back to the pre-play state. And that's actually triggered by a timer, which is the restart timer. Yeah. So we can look at how these things interact. So when the game initially begins, let's find that. So here's the initialization function for the game. Since we're going to be calling this repeatedly, all the stuff that sets up the score and the bases and the health of the bases and all that stuff, that gets rolled into a function called initGame, and we immediately enter the state pre-play. We load the rest of our resources, and then we start. And our event loop now, what we're waiting for at this point is for somebody to press a mouse button. So if a mouse button is pressed, there's two different things that could be happening. Either you're playing the game, in which case it's the old code. We launch a missile at that location that the user just clicked. Or you're in this pre-play state, in which case you initialize the game and you set the state to play, right? So user clicks, you move from the pre-play state into the playing state. if okay, so that's how that works. And if you look at the rest of the code, you will see that you don't do things like update when you're in the pre-play state. So for example, when we receive one of these refresh timers, the ones that come 30 times per second, it's only if we're in the playing state that we update all of the missiles, all of the bases and all these things. Otherwise, if we're not in the playing state, all we do is draw the screen again. Okay, so from pre-play to playing. From playing, where does that change happen? Well, that's in the update function. Remember, this gets called 30 times a second. And here, what happens is, if the health of the bases is, both bases is less than or equal to 0, then it's game over. So we change the state to game over. That takes us into this game over state. We play a game over sound. That's the sound of Pac-Man dying. And we set a timer, which is a timer that's going to send us a restart event. And the length of that timer is the length of that sound we're going to play plus 2 seconds. And we multiply that by 1,000. We multiply that by 1,000 because timers are measured in milliseconds, not seconds. So another change of units there, but this thing returns a time in seconds. Okay. Just let me get the. I want to make sure this is parenthesized correctly. Times 1,000. Convert that to an int. Okay. All right. So that then from here takes us to the game over state. It starts this timer. The timer, after this number of milliseconds, will send us a message, which is the restart message. In that case, we go back, we change the state back to pre-play there, which has us displaying the press any or click the mouse to play message. And we have to turn off that timer, or else it's going to keep sending us messages repeatedly. So if you use a timer this way, remember the timers, you tell it how the frequency with which you want to receive this event, and in this case, we want to receive it for some number of milliseconds, but we only want it once, so we have to turn it off. You turn off a timer by giving it a value of 0. So that stops us from getting more of these events. Otherwise, we just keep going back into this restart state, and you get to play the game for about 2.5 seconds, and then it would start over again. Go back to this, click any key to continue. Okay, and all of that has to be integrated into the draw function, which draws, in any case, it draws the background, it draws that thing in the middle that we call the gun, it draws the bases, it draws all the missiles that we know about, the scoreboard too, and then it does a couple of special things based on the state. So if we're in the game over state, we draw that text that says game over, and if we're in the pre-play state, we draw this text that says click to start the game, and then finally we draw the health bars. Okay, so any questions about that? Yep.
I have a question that's not about this specific because that's not pygame.
Yep.
In a lot of other courses, we kind of specify that we had to do something that was good across platform. So our code had to work for Windows, like a MacBook, and all that.
Yep.
There's been a lot of bugs with pygame on Apple,
Yep.
not MacBooks.
Yep.
Does that matter, or are the TAs going to correct it on Windows, or what?
TAs are probably going to avoid using Macs for the grading because they're so grief-filled. So should be okay there. If it's working on your MacBook, it's probably working on other things. Be careful, and I've seen the quarter resolution problem before. So don't just ignore that, at least test it somewhere else.
There's code on MacBook that won't run properly on a MacBook. If you run the exact same code on Windows, it'll run totally smooth.
That's the direction that's safe. The TAs are not gonna use computers for which pygame doesn't work. Yep.
You mentioned the quarter window problem.
Yep.
There's a way to fix that?
Yeah, the link to it in the forum. I don't know. I don't have a Mac. It comes from having a Retina display, and Retina display is reporting the resolution in one way as half the actual resolution, and there's some program xsetres or something you can use to adjust that. So if you dig through the forums, one of the Mac OS ones has a link to some thread where somebody says they were able to fix it this way. And if you've upgraded your OS recently, all bets are off. There's been problems, and I mean, that's what happens when you use an OS that's only 2 weeks old. So developers can't fix their stuff that quickly. Any other questions? So how's the game development going? So. It would be great if you had an opportunity to become real experts and know all the ins and outs of Pygames and make really fantastic games. On the other hand, this is a general programming course. Not everybody is interested in making games, so I think 3 assignments is really the max we could devote to this, and a few weeks of lectures is the max we can devote to that without losing the interest of too many people in a course like this. So I know many of you are in the game dev program, but also many of you are not, specifically because games are not your thing. If you don't like games, think of it as you're making a simulation. It's not a game, it's a simulation. Okay, so this is it. Last chance to ask me anything about Pygame. That's not true. You can ask me anything anytime, but it's the last time we're going to do it in class. All right. So now on to the meat of the lecture today. Okay, so let's define, so we're going to talk a little bit about recursion because I know some of you know about it and some of you don't know it that well, and those of you who think you know it maybe don't know it as well as you think you do. So let's play with recursion a bit. So here's a function, call it printer of n, and we'll say if n equals 0, then return, and otherwise we'll call printer of n minus 1. So we'll print n and call printer of n minus 1. So what's going to happen if I call printer of 5? So it'll print what?
Nothing.
Nothing? Yeah.
Won't it count down 5, 4, 3, 2, 1, and when it hits 0, and
Okay, so it'll count down 5, 4, 3, 2, 1, and then when it hits 0, it'll just end, whatever that means. It'll return. Okay, so let's see if that's correct. 5, 4, 3, 2, 1, and we don't print 0 because if we get n equals 0, we don't make it to that print statement. Good. How about if I move that print statement? Now what happens? Yep. It'll count down from 4.
Nothing.
It'll print nothing.
Well, it'll just return blank because will never reach the end statement. Will only return 0.
Yeah, in the back. Do you know that? Because you tested it? Okay, so it prints 1, 2, 3, 4, 5. Aha. So, why is that happening? So, I know a lot of you, think you have a good grasp of recursion, so then it should be easy to understand why this is happening. So, to really understand this, we need to know what happens when you call a function. So, let's make some pictures. So when I call a function in a language like Python or in most other programming languages, what happens exactly? It executes the code inside the function. Anything else? So is a function just like a goto? It goes somewhere and executes code? Or is there more going on? Yeah? It's not exactly an object, but it has its own scope. It's called scope. So the variables and the arguments for that function somehow have their own place to live. So what happens when we call printer of 5? Is something called a stack frame gets created. And inside that stack frame is a variable called n, and the value of that variable is set to 5. And now the code from the function starts to execute. So what does the code for the function do? It's right here. The code for the function checks if n is equal to 0. In this case, n is not equal to 0. N is equal to 5, so that's not an issue. And then it calls the function again with the value n minus 1. Well, we know what happens when we call a function. Here we are. We call this function again, so it creates another stack frame. Inside that stack frame is a variable called n, and its value is equal to 4. Okay? And then the function executes. We check if n is equal to 0. Which n are we checking now? 4. The one on the topmost stack frame. It's not equal to 0, so we execute the next line of code, which is to call printer of n minus 1. And so that creates another stack frame. In that stack frame, n equals 3, which does the same thing, calling another stack frame. In that stack frame, n equals 2, which does another thing, creating another stack frame with n equals 1, which then creates another stack frame with n equals 0. Now is where things get different. So when n equals 0, what do we do? Well, we return. So what happens when a function returns? If we call a function and it creates a stack frame, what must happen when the function returns? The stack frame for that function goes away. It's gone. Okay? So this function at this bottom of the stack here returns, so this stack frame just goes away. And now we have this stack frame. And it returns to the function that called it. And what's it executing now? Yeah. It's executing the print because we're in this is the stack frame where n equals 1 that we're in right now. In that stack frame, we executed the code already that calls printer of 0. And so now we're just executing the next line of code that comes after that, right? We called printer of 0, and now we print our value of n. Our value of n is 1. And then the function ends, which is implicitly another return. So if we look at what gets printed now, now we've printed 1, and then this thing returns. Now we're back up in the stack frame where n equals 2. This call to printer of 1 has just finished, which means we execute the next line of code, which is to print the value of n. So then that prints 2, and then it returns, bringing control back up to this stack frame, which prints 3, and then that returns, bringing control back up to this stack frame, which prints 4, and then that returns, bringing control back up to here, which prints 5, and then that returns, and then we are back at the top level, back in the interpreter. Okay. So that's why this works this way. All right. Is that clear? So every time you call a function, you get a stack frame created for that function. That stack frame holds all of the variables that are defined in that function, as well as the arguments to that function. And so that means a lot of things. One of the things is it means that the variables declared in that function and that are arguments to that function are really only accessible as long as that function is executing. Once it returns, all those variables are gone. So there's a name for that. That's called the scope. So the scope of those variables is basically their lifetime. And in this kind of example, the lifetime of the variable is as long as the function that's executing it is running, that variable is in scope. Once the function returns, that variable is out of scope. So notice this means that at the bottom level here, there was a point in this program where we had 6 different variables, all called n, all with different values, but there was one only that was the active scope at any given time. So we can have the same variable multiple times as long as they're in different stack frames. Okay. All right, so that was easy. If not, ask me a question now. So now what happens with this function? What will this do? Yeah, so let's check it. The conjecture is this will print 5, 4, 3, 2, 1, and then 1, 2, 3, 4, 5. 5, 4, 3, 2, 1, 1, 2, 3, 4, 5. So let's see why that's the case. I'll get rid of some of my x's here. Well, actually, maybe we just start over. It's worth going slowly for this. So, first thing we do is we call printer of 5. That creates this new stack frame where n equals 5. And now we execute the code for this function. Code for this function tells us that we should check if n is equal to 0, and if so, we should return. Is n equal to 0? No, n is equal to 5. So we don't return. What do we do instead? We print n. So that's where our first 5 comes from, because we print n. And next, we call printer of n minus 1. So we call printer of 4. That creates this new stack frame with n equal to 4. Well, n is not equal to 0, it's equal to 4. So we print it. So that's what prints the 4. And then we call printer of 3. N is equal to 3, which is not equal to 0, so we print that. And call printer of 2. N is equal to 2, which is not equal to 0, so we print that. And call printer of 1. 1 is not equal to 0, so we print that. And we call printer of 0. And now, finally, n is equal to 0. We just return. Right? At that stage, n is equal to 0. We just return. We don't do anything else. That brings us back to the function that called us with n equals 1. And in that function, we just finished calling printer of 0. So the next thing we do is print. Yeah. That exits the function. There are 6, this function is running 6 times right now, all at once, simultaneously. Or, each one pauses as the next one runs. So when we return with n equals 0, it's just the one that n equals 0 returns and stops executing. And the one where n equals 1 then resumes executing wherever it called that other function. Okay? Yeah. So then we get back up here where n equals 1, and the next thing that function does is print the value of n. So that prints the 1. And then it returns. That brings us back here where n equals 2. The next thing that does is print the value of n. So that prints the 2. And then back up to n equals 3, which prints the 3. And then back up to n equals 4, which prints the 4 and returns. And back up to n equals 5, which prints the 5 and returns. And that takes us back to our prompt. Okay? Yeah?
So it automatically returns once it hits the end of the...
Yeah, the end of the code in a function is an implicit return statement. It's actually returning none, the Python built-in none. Same thing with the return statement with no argument is actually returning none. Yeah?
Why wouldn't 0 be returned?
Because we didn't tell it to return 0. So is the question, why didn't we make it return 0, or?
Yeah, why isn't it not returning 0?
Because we just told it to just return with no argument to the return function. And in Python, that means return a special value called none, which is, in other languages, that's usually called null. But that's the main thing. Good? Easy to understand? All right. So here's a function called factorial. What does this do?
Takes it back forward.
So what's the factorial? There's two different versions of that function. So, how does this work? So what does this compute?
One times two times three all the way up to n.
1 times 2 times 3 and so on, all the way up to n. Or, if you like, or that's one version of it. And what about the other version? So this computes does this compute the same thing? Yeah. So this computes n times n minus 1 times n minus 2 and so on down to 1. Now luckily for us, multiplication, the order of multiplications doesn't matter. So these two things return the same value, but they get at them from different ways. One returns 1 times 2 times 3 times 4 up to n. The other one actually does n times n minus 1 times n minus 2 and so on down to 1. And in fact, if we look at it a little more closely, we can work out the bracketing. The first one does this, 1 times 2, and then times 3, and then times 4, and so on. And the second one does similar bracketing. Big pile of these guys. Like so. There has to be some dots there. Okay. So there's two versions of this factorial. We can just check to make sure that they really do what they're supposed to. Is that correct? So both of them do what they're supposed to do, thanks to the fact that the order in which we multiply things doesn't matter. All right, let's try another one. How about this? This takes a list A as an argument, and if the length of A is equal to 0, it returns 0, and if the length otherwise, it returns A plus the same function, summer applied to the elements A1, A2, A3, A4, the list A1, A2, A3, A4, and so on. So what does this do? Well, we can run it by hand and see. So let's do summer of 1, 2, 3. Okay, so we call that and we get this list, this new stack frame. A is a list that has 1, 2, and 3. the length of A is not 0, it's 3. So we take A at 0 and we add it to whatever we get by calling this function recursively on the list that has 2 and 3 in it. Recursively, this thing is not equal to, is not of length 0, so it takes A at 0, this A at 0, and adds it to this list that only has 3 in it. That's not of length 0. So this takes A at 0 and adds it to this list, which is empty. We call the function again on that list. The length of this list, we've already called it, that's what this stack frame is. The length of this list is 0, and so we return 0. Okay? So this thing here, this function, its stack frame leaves and it returns 0. Okay? Now, what's the value of A at 0 here? 3, right? If we look up the value of A, well, this is the current stack frame, so the value of A at 0 here is 3. So far we've got 3 plus 0. And now this thing returns, and it's returning 3. Now, so this thing is, well, it's returning 3 plus 0. Now what's the value of A at 0 here? 2, because this is the stack frame that's there. Okay? So now this thing is returning 2 plus 3 plus 0, so 5. Now the value of A at 0 here, this is A, starts with a 1. So then this thing returns 1 plus 2 plus 3 plus 0, 6. And then this exits, and it should return 6. And indeed, it does return 6. Great. So we've reinvented the function that adds up an array. Have we done a good job of it? Let's see. Let's call this on a big list. Let's say a list of 2,000 values. So let's add up all the numbers. Or let's start with 100. I don't know. This is one that we should recognize. So if you add up the numbers 0 all the way to 99, that's what you get, 4950. And let's go to 2000. What do you think you get? An error. You get a runtime error that says maximum recursion depth is exceeded. And every time you get an error in Python, you get a stack trace, which means you get a list of all the functions that are currently called. And we can check here. There's actually close to 1,000 of those functions being called right now. So that's our stack trace going up and up and up. It goes beyond the limit of the scroll buffer I have in this thing. So not terribly useful for us. And so it doesn't like this maximum, this depth of recursion that we did. And if we think about that, well, that's because, well, I mean, we're not sure why it happened, but if we think about how much recursion are we actually doing? Well, each step we take a nibble off of the array. We take the first element off of the array, and then we recurse on the rest. And so when we did that with an array of length 3, we got 4 levels of recursion. When we do it with an array of length 2000, we get 2001 levels of recursion. So somehow Python doesn't like that many levels of recursion. We can check to see how many it does like. So 100 was okay. 500 is okay. But 1,000 is not okay. 999 is not okay. 998 is okay. So 999 levels of recursion is allowed, 1,000 is not. Yep.
The built-in function for this, would that work for 2000, or is that gonna?
No, the built-in function is fine. The I don't know, I mean, there. That's interesting.
Your list is too big.
There we go. Yeah. So the built-in function works for really big things. Okay. Because the built-in function doesn't use recursion and doesn't use it this way. So, I mean, this is kind of a trivial example, but it's an example where just using recursion can lead to problems. And in Python, problems happen after 999 levels of recursion, which means you shouldn't write recursive functions for lists that just have this pattern of just taking a nibble off the list, maybe the first element, and then recursing on the rest, because then if the list has 1,000 elements or more in it, this thing is going to cause an error. But sometimes there are things that really lend themselves to recursion, and you still want to use it, but you don't want to have this possibility of a crash. So let's try and write this summer a different way, maybe a way that works a bit better. Okay. So, another version of this thing, that we want to sum up all the values in an array this way. And here's how we do it. If the length of the array is 1, that's easy to do. The sum is just the value of the first element. If the length is 0, then we'll use the convention that the sum is 0, even though it's not well defined. Otherwise, we recursively compute the length of the first half of the array. That's what this first thing does, right? This will give us the elements starting at position 0 all the way up to the length of A divided by 2, but not including that length of A divided by 2. And this will take us from length of A divided by 2 all the way up to the end. So this partitions the array into 2 halves, and we recursively compute the sum of each half, and we add those 2 things together. So, does this work, first of all? Do you think this correctly adds all the elements in an array? Let's try it. Works for that array. Works for that array. So, Good. Seems to work. How big can we go? Maybe we can go more than 1,000 with this. Yep. Can you go twice as big? Let's see. So before we could not even do 1,000, right? So twice as big. 2,000 is at least twice as big. No problem. Can we do 20,000? Can we do, I don't know, 200,000? Yeah.
It continues to split each one into chunks, right? So if it's all in a bunch of different chunks, can it continue breaking down those chunks until it's basically just handling each space individually?
Sort of.
So because each chunk is like 2,000, each chunk is like 10 or something, let's say, then it doesn't really have a problem.
Well, we'll have to look at the recursion tree, but here I just did 2 million. And in fact, this thing, before it has any recursion depth problems, it'll run into the same problem as the other one. It'll have a memory error because it can't create this range that's big enough to cause this thing to have a recursion problem. So let's take a look at this, the recursion here, and see how deep it actually gets. So let's start with a simple example. An array of length 4. So we'll call sum or 2 of 1, 2, 3, 4. Okay, so that, when we call that, creates a new stack frame. Inside that stack frame, A is equal to this array, 1, 2, 3, 4. So the length of A is not equal to 1 and it's not equal to 0. So we end up in the last thing where we make a recursive call. So what's the recursive call that we make? Yeah.
Split in half again?
So we make a recursive call here on the first half of the elements in A.
Won't that just keep splitting it with each, it's just a bunch of things that are like 1?
Well, let's see. Yes. So now we're making a recursive call on the first half of A. A equals 1, 2. So this length of this array is not equal to 0, and it's not equal to 1. So it's going to go down to the bottom and make a recursive call on the first half of the array. In this case, A is the array that contains only 1. Now the length of this array is actually just 1, and so it returns that value, 1. So this thing exits and it returns a value of 1. What happens next? Yep. So now we're back up in this execution where A is this array with 2 elements in it. We have just called this piece of code. We've just added up all the elements in the first half. Now it's time to add up all the elements in the second half. So that's a recursive call with an array that contains only a 2. That's an array of length 1, so that immediately returns the value 2. Now this thing can finish. It can do this addition operation and add these two things together, giving 3. So this thing returns a value of 3. And now what happens? The other side. Now we're back up at the top. We have just solved recursed on the first half of the array, the one that contains 1, 2. So now we recurse on the second half. So now we recurse on A is equal to 3, 4. Well, that's neither of length 1 or 0, so it's going to recurse on A equals 3. That is of length 1, so it just returns immediately and returns the value 3. And now we're back up here. We've recursed on the first half, the 3. Now we recurse on the second half. The 4, which is an array of length 1, so it immediately returns the value 4. Now this thing is done. It just adds its two results together and returns the value 7. And now this thing is done. It has its two results. It adds them together and returns 10. Is that clear? So what's the recursion depth here? In this case, how many stack frames did we ever have on the stack at any given time? 3. There's a lot of stack frames. In fact, there's as many stack frames in this as the previous function, but they're organized differently. We only ever had 3 of them at any given time. So, initially we started with these 3, up to here. And then this one returned, and we put this one on, and then this one returned. But never at any time did we have more than 3 of them on there. Okay? That's good, but that doesn't really tell us much when the length of the array is 4. So let's abstract this picture a little bit and think about what happens when we call this on an array A, and the length of A is equal to n. And n is something big. Think of n as something big. So, well, if n is big, it's bigger than 0, and it's bigger than 1, so we'll call this on another array of length n over 2. Right? That's the first thing we do is we call it on the first half of the array. Now, we'll call it again. If n over 2 is still bigger than 1, then we'll call it again with an array A, whose length is n over 4. If that's still bigger than 1, we'll call it again on an array whose length is n over 8. And this goes on for a while until the length of this array is less than or equal to 1. So how long does this take?
Would be the log of n
Yeah.
plus 1.
So there'll be it's about the log of n, the binary logarithm of n. So how many of you know about logarithms? Yeah? So what's your definition of a logarithm? So, I mean, the usual definition you get is something like the log base b of x is the solution to the equation b to the, or let's do it this way. Log base b of n is the solution to the equation b to the x equals n. So solve for x, that gives you log base b of n. That's not a way I like to think about logarithms. It's not a particularly useful way to think about them in computer science, because the way that they usually come up in computing is thinking about how many times you have to divide something until it becomes smaller than 1. And this is exactly an example of this. we start with n here, and we keep dividing it by 2. And we keep doing that until the result is smaller than 1. And that's actually the height of this thing, then, is log base 2 of n. Plus or minus a 1 because we're dealing with integers here, but that's the way to think about logarithms most of the time when you're doing computing, is how many times can I divide n by b until I get a value that's less than or equal to 1. That tells you the logarithm, plus or minus 1. All right, so this says that this thing will go down to the bottom and start returning after log base 2 of n steps. But that's not over at that point, right? Then it still has a lot to do after that. It's still gonna, this is gonna return, and it's gonna make another one over here, and this is gonna return and make another one over here, and this is gonna return and do another one over here. And so we actually get this giant, what's called a binary tree, a recursion tree of these things, where down at the bottom, down at the very, very bottom, are little arrays here of length 0 or 1. And then they're all joined up in little pairs, growing up in pairs like this, all the way up to the root. So, tell me something about binary logarithms. So, what's the log base 2 of, I don't know, a million? It's about 20. 20 or 21. What's log base 2 of a billion? It's about 30. So even if we pass this thing an array of length 1 billion, the recursion depth is only going to be 30. So there's no way we'll ever get to a recursion depth that exceeds 1,000 here, because to do that, we would have to pass it an array of length 2 to the 1,000. How big is that array? Well, Python will tell us. 2 to the 1,000. That's how big that array would have to be, how many elements we'd have to pass this thing before we blew up the recursion depth. We don't have enough memory for an array like that, so we're safe here. Okay? So, just a couple of takeaway lessons then from today is, recursion is tricky very often until you get used to it. The way you understand what a function is doing recursively is by drawing these pictures of what's happening with the recursion. And these pictures aren't always simple. These pictures are not just not always straight linear pictures where you have, a recursion stack that grows down in a line and then everything returns. If you make more than one recursive call, you end up with pictures like this. So if you have 2 recursive calls, you end up with this binary tree. And often by changing the way you do your recursion, these 2 functions basically do the same thing. They just do it in a more balanced, one does it in a more balanced way, and it's the difference between night and day in terms of recursion depth. I mean, it's the difference between a recursion depth of a billion and a recursion depth of 30. So a billion's not going to work for you, but 30 is fine in just about any language. So that's probably a good place to leave it for today. Good luck with your assignments.